Thank you for the invitation. This is a great honor to be here. I keep hearing about Purdue and Sirius in the news all the time, so it's a great pleasure to be here and see the operation of your lab. Security is so important. It's really nice to see a center devoted to security, so I really appreciate the invitation. The talk today is about security and voting systems, so it's a focused application of security, and one of my goals here is to get you interested in this as a research area. So part of this talk is as much about the problem and some things as it is about results. It's not really so heavy on results. It's sort of thinking about the problem, what it's like, and maybe get you motivated to think harder about it as a research topic. Because we need work in this area. Voting is not a solved problem, far from it. It's a sort of a mess right now. It's a hard problem. And if you like messy, hard problems, this is a good one to dive into. So we'll talk a little bit about voting first, and then a little bit about voter-verified paper audit trails, and then voting with cryptography, which is maybe most of what I'll talk about, trying to give you some of the ideas about how cryptography might be used to come up with better voting systems. I say might because there's all other kinds of issues like usability considerations and so on that come on there too. And maybe if there's time, I'll tell you a little bit about some of the issues that come up in the voting standards work that I'm doing, which standards is usually sort of boring, so I won't say too much about that. But we'll talk a little bit about some of the issues that we try to do there. So the goal is, how do you make a good voting system? How do you make one that you can really trust? So it's an important problem, and it's an easy problem until you consider security. I mean, just adding 1 and 1 and 1 and 1 and 1 and 1 and 1 is not hard. But making sure you've got the right ones to add and that nobody's tampered with the ones and made them zeros is the hard part. There's a wonderful book about the history of election fraud in the US by Andrew Gumbel called Steal This Vote. And if you want to just have some good nighttime reading, that's fun. It talks about election fraud, the history of election fraud in the US. I like this anecdote here about the governor of Louisiana who wanted to be buried in his home state just so he could stay active in politics, because there's such a long history of dead people voting in Louisiana, that's not the only state where that happens. So. I think nice quotes like Boss Tweeds and Stalin saying, those who vote determine nothing, those who count the votes determine everything. And you'd like to the extent possible, make that false through good work in security. So voting technology is changing. We have up here the early diagram from Thomas Edison's patent on voting systems. He proposed a voting system for the use in Congress, which they didn't like because it gave the results too quickly, and Congress didn't like that. And here's Judge Rosenberg from the Florida election counting, as you may remember. So voting has followed ordinary technology trends, and that's to be expected. You make use of whatever the best technology is. Greeks had dropping stones or shards of pottery and bowls, paper voting systems you may have seen or used. Lever machines have been popular in New York, punch cards, OpScan. We're getting to the stage of computerization now. Everything's becoming digital. Why not voting becoming digital? What can we do to make this technology, make this problem make use of all the nice computer technology we have? So punch cards are out. We need to replace them. A lot of DREs are out there. They seem to be meeting quite a bit of skepticism, perhaps rightly so, and a lot of people requiring voter-verified paper audit trails on those machines now. So the question is, what's possible? What can you really do with all the technology we have? Can you make a voting system that doesn't require paper, say, in some way? What kind of electronic voting systems are possible? What can you really make secure? So the answer to that, I don't know. I mean, what we're exploring, and I'll give you some ideas. Here's what voting looked like in the US in 1980. The blue is lever machines. The red is punch cards. The orange is paper, hand-counted paper votes, and so on. So it's a mix. Voting is a mess from a business point of view because every county gets to buy its own voting equipment. The poor voting machine vendors have to make all these trips to every county in the US. 5,000 of them or whatever. Today it's changed a bit. The green is OpScan. You fill in the bubbles. Purple is DRE, electronic. I guess you guys are a mix. I don't know what you are right here. What do you use in this county? DREs, yeah, okay. New York, I guess, was still lever. So even they're moving out of that now, of course, as HAVA gives them money to move. So it's changing, and it will continue to change. The technology changes, the vendors build new stuff, the standards change, and our sense of what's secure changes. So it's a complicated, funny business. There's lots of things happening. The Help America Vote Act of 2002 gave $4 billion to the states to upgrade their equipment. So the states are trying to figure out what they should buy. Avi Rubin at the Johns Hopkins is leading a project together with others, which got $7.5 million from the NSF to study better voting systems. At MIT, we're working with Caltech. We've got the Caltech MIT Voting Technology Project, which put out a nice report a couple of years ago if you want a good introduction to voting research. That's a nice thing to read. As was noted in the introduction, I'm on a standards committee, the Technical Guidelines Development Committee, that's part of the HAVA legislation to develop new standards for voting systems. So got the challenge of how do you specify standards for voting systems in the face of all this change and difficulty. There's a lot of activist groups. There's very serious commissions like the Carter-Baker Commission studying the problem. The General Accounting Office came out with reports and so on too. There's lots and lots of activity in voting. If you want to get involved in this, and there's lots of reading, go to my website. I've got lots of links to a lot of this stuff. So the Carter-Baker Commission proposed voter ID cards, for example. There's many different things that need fixing. Not only the voting machines themselves, the voter registration databases are a good source of fraud if you're going to try to fix an election, just disqualify a lot of people from voting, et cetera. So lots happening, and I'm not going to talk about it all. It's a hard problem. So here's some of the pieces. You need to have a voter registration system so that each voter, you know who the eligible voters are, and each voter votes at most once. Voter privacy is probably the most important and most difficult aspect of this problem. This is what makes it different, voting different from almost any other problem you may look at, like electronic commerce. You can't allow the voter to walk away from the voting booth with any kind of proof as to how they voted. You can't give them a receipt like an ATM receipt because they will sell it, or some of them will sell it. You want my vote for 20 bucks? Sure, show me the proof, whatever you do, a little transaction. If you read Gumbel's book, there's a long history of this in the United States of selling your vote. So we'd like people to vote honestly. We don't want to provide any mechanism for them to sell their votes or be coerced. I mean, their boss shouldn't see how they voted. Their spouse shouldn't see how they voted. Their pastor shouldn't see how they voted, whatever. I mean, people should vote privately. That's a very important principle in voting. And it's the one that really makes this problem different. Because the kind of records you want to keep, you just can't keep sometimes, it seems. Of course, you need the usual integrity. The votes can't be changed, added or deleted. Everything's accurate, availability. So the usual system requirements. The system should be up and available when you want to use it. Should be easy to use. This is a set of requirements that are coming along quickly now. The Help America Vote Act talked a lot about making sure every precinct has a place where a disabled person can vote. So there's lots of parts to this problem. So it's got many requirements. It's one of the more complicated problems you'll see, just because it really interfaces with everybody. And these are not all the requirements. There's lots of other ones, as we'll see too. When you think about, if you focus in on security, which is where my interest lies, and say, well, how do you start thinking about security? You have to think about who the adversaries are. So you've got people who work for the parties who want to fix the election, some political zealots, maybe foreign powers. Maybe the election gear is even made overseas. What about that? Who's got motivation there to tweak the hardware in certain ways? Who knows? The voters are potential adversaries. They may wish to sell their votes. The election officials. In many states are partisan officials. They belong to one party or another and may be biased. The vendors may have a programmer that's gone bad inside or has been corrupted. So really, almost anybody is a potential adversary in this system. It's hard to think of anybody who's sort of not potentially corruptible to somebody else's end. So you want to design a system with enough checks and balances that the thing still works. Electronic voting, is it trustworthy? Well, who knows? That's part of the problem is not so much whether it's trustworthy, but how do you tell if something's trustworthy? How do you certify a system? Diebold's been having problems with their equipment. A number of the source code's been revealing all kinds of problems with key management. That was a few years ago. More recently, there's been some studies with some of the Diebold equipment. In fact, it's being examined right now in California for if it's there, it's really a giant loophole in the Diebold OpScan system, where the Diebold system looks at the memory cards put in for code to be downloaded before it actually runs the election. I don't know if it's there or not. I haven't looked at the system, but it's alleged that that hole is there. That would be a major problem if it's really true. These systems are getting more and more complicated because they need to be fancy to help guide people through the elections. The U.S. runs the most complicated elections in the world. We have more candidates, more races, more questions asked of the voters. You need to have a good GUI to make all this stuff work nicely. They're a complicated system. There's lots of them out there, lots of these systems out there. You know, one voting system might handle 300 people a day, so election days. You got to have lots of systems out there. The people that run these systems are typically blue-haired old ladies or the like. You know, people that have been running the old systems for a long time, semi-trained. The certification process is not set up yet to, or maybe never will be, to really verify the security of these systems. So you end up with the question at the end: is the vote you cast the vote that was recorded for you? And you know, at this point, you know, the answer probably is, well, we hope so, but you know, there's no proof that you got it. And you can ask the question: is there some way to get the proof you'd like? So there's some proposals for trying to work on this. So one is voter-verified paper audit trails. And I'll talk about that just briefly. And then there's the question of cryptography. What can you do with cryptographic techniques? And I'll talk about a couple of approaches, one based on mixed nets, and a related approach that's new to one of the students that's in our group at MIT, Benedita. And we'll talk a little bit at the end about voting system standards. So this is an area, as I said, which needs a lot of research. It's a hard problem. There's no magic bullet for it. You need to have sort of an approach that thinks about the entire ball of wax to make progress. But you know, cryptography can help with some of the accountability and integrity issues. So the idea of a voter-verified paper audit trail is due to Rebecca McCurry, I think. It originated with her and Peter Neumann in her PhD thesis. So the idea would be that a voting machine should produce a paper audit trail that the voter can inspect and approve, so that at the same time you compose your vote, maybe on a touch screen, then the machine will produce a paper record that you as the voter can look at and decide that if you like it. If it's a good record of what your choices are, you push the button that says cast this vote, and it will then cut it off and dump it in the ballot box. If you don't like it, there was some way of spoiling the ballot, marking it as void, starting over, getting another printout. That's the idea. It's not it's clearly got some merit to it, right? It's clearly something which gives the voter some more assurance that there's some record that he can trust that looks the way he wants it to look, because you know, unlike with just a pure electronic system, the voter can't see the bits that are being recorded on the memory card at the end. And here the voter has some direct ability to verify the record with your own eyes, assuming you're a sighted voter. And blind voters got issues here, but that's one of the issues that the standards have, is what do blind voters do for paper trails, and that's sometimes they go back through a scanner or something. The voter-verified paper audit trail then becomes the official ballot. There's lots of problems with this idea, lots of benefits you can get as well. You know, the voter-verified paper audit trail can be the efficient ballot in the case of recounts. It's been adopted in California and other places. David Dill's been very instrumental in getting this adopted. But there's you know, some issues that we might as well identify. You know, you still need to guard the printed ballot. Somebody can change the electronic records and then also change the paper records as well to correspond. You know, possession is still required. There's this two-step voting procedure. You compose your vote on the screen, and then you have to look at the paper trail as well to see that it corresponds. And actually, most people don't care. They won't look at the paper trail, or many of them won't. So depending on how you set it up. So it's a real question of engineering usability for this system to make this as nice as you'd like. But a lot of voters just don't look at it. Ted Selker at MIT is looking at audio trails, which people tend to pay more attention to. But then you don't have a tangible record. It doesn't catch all the problems. There may be some candidates missing from the slate. You know, a voter can say, you know, hey, this voting machine isn't printing out what I chose, or this machine cast the vote even though I said don't cast the vote. You know, it could misbehave in other ways. So voters can cause a denial of service attack by casting suspicion on the voting machine. So you don't have, with voter-verified paper audit trails, really end-to-end security. That does help the voter be content that his vote was cast the way he intended it. The voter sees the piece of paper and can see the piece of paper go into the ballot box, representing his choices properly. But it doesn't help ensure that the votes are counted as cast. And to have a good voting system, you really want to have end-to-end security. You want to have not only cast as intended, but counted as cast. And once it goes into that ballot box, who knows what happens to it after that. You're trusting the election officials. And most election officials are honest, but you have to worry about that part of it. You're putting some trust where maybe you can apply some technology to get around it. So let's talk about voting with cryptography. So there's a long history of this, actually. Josh Benalow at Yale did one of the early theses back in the 80s. And there's been a large number of proposals. There are basically three categories of proposals. So this is a big literature. The first category is blind signature-based voting systems. So you have, in all of these schemes, you have the idea that a ballot is a piece of ciphertext or a sequence of bits that's signed or encrypted somehow. In the first case, you want it to be signed by, well, not the voter themselves. You can't sign. I mean, if you had a public key infrastructure, you could imagine having everybody signing their own vote, right? So you take out your digital signature and you sign the ballot directly. So what's wrong with that? Well, then you've got a record as to how you signed. You've even got a digital signature. So you've got to worry about the anonymity, the voter privacy of that. So to solve that problem, to have voter privacy with signed digital ballots, one category of proposals is that you use a blind signature technology. So RSA and other signature schemes support this blinded signature possibility. So if I want Gene to sign something for me, I can give him a document that's been blinded that he then digitally signs, and then I get it back and I can unblind it. So the two operations of signing and encrypting sort of commute, and you can take off the encryption without taking off the signature. And so I can get a signature by an election authority on my ballot. So the election authority is signing everybody's ballots without seeing anybody's ballots. That's cute. So using a little mathematics there to do the encryption, signing, decryption. The signing stays on. You submit that. You have to submit that anonymously, of course, still. But then you've got a ballot that's signed by the election authority. And so the process of checking people off as having voted is done by the authority who's signing the ballots for you. And that sort of works. You've got the problem that the authority is signing all of the votes, and so he can stuff the ballot box. You have to worry about that. And you still have to implement this anonymous channel for depositing your ballot once it's signed. Other approaches follow one of these other two categories, either homomorphic encryption or mixednet. So let's talk about them in turn. So homomorphic encryption makes use of other mathematical properties that some of these schemes have. So with homomorphic encryption, and the best example of this is the Pierre scheme, you can take ciphertexts and add them together while they're encrypted. So you use some lovely mathematics that says that the product of two ciphertexts, EA times EB, is itself an encryption that represents the sum of A and B. Right, so you multiply the ciphertext together. So EA is a ciphertext representing some number B, some number A. E and B is some ciphertext representing some number B. You multiply those together, you end up with a ciphertext representing their sum. So you can add numbers together by multiplying the ciphertext without decrypting. So you vote for your favorite candidate, and you submit an encrypted 1 or encrypted 0. So does everybody else. They submit their encrypted 1s or 0s for the candidate. So how many votes you're casting for that candidate. So it should be either 0 or 1. There's an issue there. You've got to prove that it's either 0 or 1 without decrypting it. But given that anyway, which is easy to do, then you could just take all of the encrypted 1s and 0s and add them together to get as you multiply the ciphertext together to get an encryption of the addition of all the 1s and 0s. So you can do the counting while encrypted. Very cute idea, right? So you can take ciphertext for everybody's vote. So you say how many times you vote for each candidate and prove that you're only voting once for one candidate and 0 for everybody else. Then you take all these things and multiply them together. You end up with a grand total. You get the grand total still in encrypted form without having decrypted anything. Then you have a trusted authority or collection of authorities decrypt that, and you have the grand totals. That's a very cute scheme, right? That's nice. It almost works. I mean, it does work in some countries. It doesn't work in the U.S. because in the U.S. you're required by law to have to allow write-in votes. If you're voting for president, you're allowed to vote for Mickey Mouse for president every year, every time they have an election. It's mandated. A voting system must support that. So if you didn't have that, and some countries don't have that. Some countries say if you want to be a candidate in election, you've got to get the right number of signatures ahead of time to get on the ballot. And the only people you can vote for are those people on the ballot, right? So that's fine. And the system actually is not a bad match. In fact, the system was proposed in France, Paillet's French, so that where they have more of those kinds of laws. But in the U.S., you have to allow write-in votes. The kind of encryption scheme you have here is, with Paillet is the number A is encrypted as G to the A times R to the N, where R is random, mod N squared, N is like an RSA number, product of two primes. And so when you multiply these things that look like this together, the G to the A and the G to B give you G to the A plus B, and you end up with the homomorphic property you want. So that's cute, right? And it almost works. So you cast your vote. I mean, the key idea here persists in the next idea too, which is that your vote is a piece of ciphertext, right? So that using crypto seems to involve this idea, or will involve this idea of transforming your ballot from a piece of paper or whatever to a string of bits that's an encryption of your vote somehow. And here the encryptions satisfy this nice property. So you cast your vote, your ciphertext is maybe posted on a website together with your name even, right? You could do that, right? You could take all your ciphertext, just to think through the possibilities here. You could have your ballot be on a website next to your name. It's a bunch of encryptions of ones and zeros, how many times you're voting for each candidate, a little bit of a proof you have to give, and I'm not saying how to do that, but you have to show that you're not voting twice for some candidate and you're only voting at most once for some candidate. And then, then anybody can multiply all these things together to do the tally. The trustees do the decryption. So that style persists here with the mixednet approach, which doesn't do the adding until after the decryption is done, and does a different technique for achieving the anonymity. So David Chaum proposed this idea of mixednets, which involve a number of servers whose primary goal is just to mix up the votes, to scramble them, to shuffle them, and to provide anonymity for the voter, right? So that's the one property we want to maintain. And so this is a different architecture. And it does handle write-in votes because in this scheme, the ballots can be arbitrary. So the current flavor of voting with mixednets has really been pioneered by David Chaum and Andy Neff. Andy Neff actually has a company in Washington State called VoteHereNet, which is trying to make a business out of this. I think he's doing okay. I'm not sure details. But in any case, the official ballot for these schemes, you've got an electronic ballot. So the ballot is a piece of ciphertext. It's no longer paper. And the ballot is the encryption of your choices. So you create some document, some record that says what your choices are. You encrypt that with a public key scheme, with the key of the eventual trustees that are going to decrypt it. So your ballot is a piece of ciphertext. And that may be posted on this public bulletin board, as I said, next to your name. So we've got a public record of how everybody voted in a form that can't be used to buy votes, right? Because it's all ciphertext. So you can't say, Ron Rivest votes in a bunch of gobbledygook. That's the encryption. So I can't use that to sell my vote because nobody else can read it. Right? So you can post it. I could even get a piece of paper that has the same gobbledygook on it as I walk out of the voting booth, and I could use that as a check on the bulletin board to make sure the bulletin board's not changing my vote. So the receipt I get is a different kind of receipt than the paper receipts we talked about earlier. It's a receipt that's a receipt for the ciphertext, and the ciphertext is what is officially cast as my vote, if you will. Okay. So I can use that, detect voting machine error fraud, so we can use that for these purposes, but not as an official ballot. Okay, so that's the high-level picture. Let's go into some of the details. So there's a couple of problems, as we saw, with voting. One is that you want to have checks that things are cast as intended, and the second is that things are counted as cast. So we want to solve both of these with these problems, or at least attack both of them. So let's look at them in order. So let's take that first process. So we've got the process of I go to the voting booth, I type in my choices. There's some ciphertext produced that allegedly represents my choices. So what reason do I have to believe that I'm not just being totally defrauded at that point, right? I mean, it might be that this voting machine has encrypted some other choices. I voted for A, it's giving me a piece of ciphertext that encrypts a vote for B. I'm not a computer. I can't check this stuff very well, right? So I'm a person. Right? The early voting literature didn't make that distinction. The early voting literature, if you look at it, sort of assumes every voter is a person. Says, start off with the voter picking a 1024-bit random number and doing some modular exponentiation in your head or something like that, right? So the literature's matured since then, and we no longer assume that voters are capable of doing modular exponentiation in your head. All right, so the voter is a human. How does the voter, I mean, maybe the voting machine is doing modular exponentiations and so on. Probably it is. But how do you check that those are being done properly? So that's not easy, and that's one of the hard parts of this. And we're only sort of hanging on to this part of it with our fingernails, so I think. It's challenging. The voter can't compute, and she can't take away anything that would allow her to prove how she voted. So she needs to take away some sort of evidence that would allow her later, maybe as she's exiting the polling area, to detect whether cheating occurred. And she also gets this receipt as to what her ballot is. So this is hard to do well, and this is one area where research would. So let me give you a couple ideas on this. So I'll give you two approaches to this, and I hope that you'll at least come out with the idea that if somebody's calling me on the phone, I should kill this thing. Never mind, I'll just ignore it. So we want to have some argument that the ciphertext you've got is what you want, right? So here's one approach, a cut and choose kind of argument. View the process there that the voter's in as one of doing an encryption, right? So basically that's all that's happening. You put in your choices, you get an encryption out. How do you know this encryption box is doing the right thing? Well, you won't inside the voting booth, but maybe you can tell later. So let's imagine you sit there and you make up several choices, maybe two. So you type in choice A and choice B, one of which is your real choice, one of which may be some other choice. And you get ciphertext for both of them. And then the machine commits to those two pieces of ciphertext. And then you cast one of them as your vote. And then the second one you get a proof for. So the voting machine will reveal the random numbers used to do that encryption. And because it's a public key encryption, so the public key is known, but these are randomized encryption schemes, so you always have some random number that goes into it as well. And if you see that random number, you can check. You can do the. Gene, you want to kill this for me? Let's turn it off. Thanks. So you get two of them. So it's basically you got an operation which takes an input, puts an envelope around it. So you want to check that things are actually ending up in the envelope. You can test it. You put things in. Are you getting an appropriate envelope at the output side? You can just check some of those. But you need to do some computation. Maybe the ACLU runs a booth there too. You put your numbers in at the end to check that the random number's there. It's a little awkward, but it's doable. So with probability of half, what you end up with a proof is not your vote. That's the important thing, right? So you're getting a proof of the encryption of something that's not your vote, and then your vote you don't get the proof for. It gets deposited, but the machine didn't know which one you were going to deposit and which one you were going to get the proof for. So you've got at least a probability of half of catching a machine that's trying to cheat you. Okay, and that'll be if a machine's trying to cheat for a large number of votes, that should be fine. Here's another approach. Maybe this will be better. This is due to Peter Ryan, called Prêt à voter, ready to vote, right? There's a pun on some French food chain or something. So he proposes that you have the following structure for this first part, where you're trying to get confidence that the votes are indeed done in a way that truly represents your choices, but in a way that you can't carry away a proof. So the ballot, you use, start off with a piece of paper, which might look like this. You have on the left-hand side the candidates' names. So there's 3 candidates, there's 3 rows. It's blank on the right except for the bottom thing, which has got some seed number in it. And so you put an X next to your candidate. So the idea here is that these ballots are pre-printed. Every ballot is different. Every ballot has a different seed number. The seed number determines via some encryption process what the order of the candidates is. So this 3, 2, 5, 6, 8, 9 determines that the order will be Smith, Jones, Kent, and not Kent, Smith, Jones, or something else. So this is an encryption of the permutation there. So when I put my X there, you know, voting for Jones for some people might be in the middle, might be the bottom, might be other places. So the order is always changing. Actually, something like that's required by law in many states. There's a 5% advantage the first person on the list always has, just because people are lazy and they don't know they picked the first one. You know, so if your name starts with A, you've got a better career as a politician than if your name starts with some Z thing. You know, so but states try to randomize it. So, but that's a separate set of issues. That's psychology. Here we're talking about security and crypto. So the reason here is we want to just have voter privacy. So you vote with your X, and then we're just doing one race here. There may be lots of races, and so it gets complicated with lots of pieces of paper or you know, big cutting machines if there's more. But anyway, so then you cut the paper in half, or you tear it along a perforation vertically, and you destroy the left-hand side. And you've got the right-hand side, which is what you deposit in the voting booth. And maybe you can get a photocopy of that and take away your receipt of the right-hand side. All right, so that's your piece of ciphertext. The right-hand side is your ciphertext. And that's sufficient to recreate your vote, actually, right? Because knowing this number, the trustees can know what the order of the votes is, and then they can figure out who you actually voted for. So the right-hand side is sufficient information for the trustees to do this. You have to make sure that people don't walk out, you know, make a photocopy of the entire ballot or walk away with the left-hand side. A lot of these schemes have this property that you're forcing the voters to leave something in the voting booth, and maybe that's hard from a usability point of view. So you end up having this posted on the website as your vote, and then there's a process of anonymization for that, which allows you to have a number of trustees scramble the order of the votes to decouple this from your name, and then finally use this number, or actually a decryption of this number, to reveal what the order would have been. So some details there that are non-trivial, but in fact you can make that part work as well, so that you have a cooperative process for a number of trustees to decouple the binding of your name to this vote before this is decrypted to come up with that list of candidate names. And so there's that process there, and mixed nets are used there as well. So mixed nets are used in either of these schemes to actually do the anonymization. So that's the end of my slides on this first part, which is having some confidence. Oh, I didn't talk about the sampling. These ballots could be made up fraudulently, right? They're pre-printed. You need to have some prior testing or something like that just to check that the things are being done properly. So you need to have somebody picking random ballots at the beginning of the day, checking that this number really does correspond to that order and so on. So you've got to have some protocol for working with the trustees who hold the secret key that corresponds to this encryption and check that this order corresponds. Not easy, but doable. Okay. So these two things, this is solving a really hard problem here. I mean, it's one that deserves more thought, and we need better techniques. You know, how do you develop some confidence that your encrypted vote really is encrypting what you want? From here on, it's downhill. It's actually easier, right? But this part is hard because you're trying to, you know, it's what is in my head, which is not digital or anything like that, correspond to what's encrypted, which is a pile of ciphertext. That's a hard question. So some kind of little song and dance and protocol seems to be necessary there. But it seems doable. These are workable ideas. And you know, I think with more thought, we can come up with even better protocols for telling that your cast vote, your piece of encryption, really does correspond to what you want. And then from then on, as I said, it's easier. It's not totally easy, but it's easier. So here's the high-level picture of voting with mixed nets for all of these schemes. You start off with some process of encrypting your vote. So the voting starts off on the left-hand side, and this box labeled E here, this orange box, is what the encryption that happens that we just talked about at the voting machines. And then maybe that gets, I had a laser pointer, maybe I still have it somewhere here. But you have a serious mug. There we go. Does it have a laser filter? Better be careful. All right, so we have, so this is the voting booth. This is your plaintext vote. You compose that at the machine. Then this is your ciphertext that you now happy is really represents your choices. This is the first list of things. So next to your name, you know, say Jeff Vetter voted and then it'll give you ciphertext, and Gene Spafford voted, whatever, give your ciphertext, and Ron Rivest voted, whatever, gives my ciphertext. So we've got a list on the bulletin board listing everybody's choices, and because of the song and dance we went through, we all have some confidence that those really represent our choices. Now we want to decouple those ciphertexts from our names and count them. So this process are all the mixed servers that are going to scramble the order, and we have a final decryption. And we can then decrypt all of these to get the plain text choices back again, but in a way that's dissociated. So this is the encryption operation. These are mixed servers. Each mixed server permutes the inputs, so maybe the first input comes out the second line and so on. So it does some secret permutation. The composition of a bunch of secret permutations is a very secret permutation, right? And then we have this very secret permutation posted on the web again. They're finally decrypted and published, and anybody can add them up at that point. Right? So we've got encryption, mixing, and decryption. So now we need to have evidence that the votes are counted as cast. So we've had evidence that the votes were cast as counted with this kind of approach. So what can go wrong? Well, the mixed servers themselves may be administered by partisan parties. I mean, maybe one is run by the Republican Party, one is run by the Democrats, one is run by the ACLU, one is run by the League of Women Voters. Maybe one of those parties is corrupted somehow or malicious. So they might be dropping ballots on the floor and replacing them with other ballots. They know the public key. It'd be easy for them to make up other ballots that look good. So we need evidence that none of the mixed servers are doing that they're behaving. So these are nice computations, though. They at least have public inputs, public outputs, some secret parameter that affects the permutation. But at least it's not dealing with the other problem, which was really hard, which is telling that something that in your head corresponds to something that's on a piece of ciphertext. There's a ciphertext corresponding to ciphertext, so this is much more tractable. But they can't reveal the permutation they're applying, so they can't say how they scrambled the votes. So they're each taking a metaphorical big bucket and shaking it up, but they can't say what the order is. And at the end, we also have to make sure that the trustees who are doing the decryption are doing that properly as well, because they could lie about, so this ciphertext represents a vote for A when it's really a vote for B. So there's a bunch of proofs that these agents need to come up with. They need to prove that they're doing things correctly. So these mixed servers need to produce proof that they're doing the right thing and not dropping votes without revealing the permutation. The decryption server needs to reveal that they're decrypting things properly. That's actually pretty easy to do, because you decrypt, you get the randomization factors, you just exhibit those, and it's easy to re-encrypt and see that works. The mixed servers is a little more complicated. Let's talk about that. So how does a mixed server prove that he did the operation correctly? So the operation he's supposed to do is what? He's supposed to take a number of ciphertexts in, reorder them with some secret permutation, produce a number of ciphertexts out, and also re-encrypt. So you need an operation where you can re-encrypt or re-randomize at least, because if the ciphertext isn't changed in terms of its bit pattern, you can tell if this looks identical to that. The permutation is obvious. So you need not only to permute, but also to re-randomize. So you need to produce a new ciphertext which represents the same plain text as the original ciphertext, but has a different randomization factor, so the ciphertext looks different. And it may be done in most cases without even knowing the secret key for that public key encryption, so you're just using the public key. So this turns out to be doable. You need a proof that's produced that this operation is done correctly. What kind of proof should it be? So we want anybody to be able to check this proof. So anybody can look at the website, see these ciphertexts, see these ciphertexts, see this proof, and say, yep, those ciphertexts encrypt the same set of votes as these ciphertexts. Be convinced of that without actually knowing what the correspondence is. So that proof shouldn't reveal what the correspondence is. So there's actually a large literature on this problem. Let me mention one approach that was developed by myself in conjunction with Marcus Jacobson and Ari Jules, published a couple of years ago. It's pretty easy. It's a probabilistic kind of checking thing. And the idea is it forces each mixed server to reveal and prove half of its input-output correspondences. Right? So we want to challenge the mixed server to match up some of the outputs inputs. So just as we saw, you could have a decryption server prove how it worked. Once you've got the particular input and the particular output, it's easy to prove that corresponds. But we'll do this in such a way that no voter's anonymity is violated. So here is an example. So we'll pair up the servers. So here's the first mixed server, maybe run by the Republicans. Here's the second mixed server run by the Democrats. We'll pair them up. the Republican server puts this list of ciphertexts on the website, and based on some pseudo-random hash of everything that's on the website, will challenge the Republican server to produce the input that correspond to the first one and the second one and maybe the fourth one and the eighth one or whatever. So some subset of the intermediate values will be challenged, and the Republican server will have to reveal the input that correspond to the first output and reveal the input that correspond to the second output and give the corresponding re-randomization factor so that those proofs are easy to do once you know the correspondence, but only for half of them. And then for the other half, it will be the Democratic server that has to reveal the correspondence. So the Democratic server will have to say, well, the third one, where did that go? Prove that this one, show me which output it produced and show me what the correspondence is. Okay. So these challenge bits to say which way it gets challenged are produced in some totally independent way, say as a hash of everything that's on the bulletin board. You get some random bits, you use those bits to run these challenges. So these servers are challenged. So no voter's vote is ever going to be revealed all the way through, because if it gets revealed on if you see that the second voter corresponds to the first intermediate result, that intermediate result will not be challenged here, and so you won't know which of the outputs, at least which of the other four outputs here that weren't challenged here correspond to this vote. So you have at least an anonymity of half the voters. So you don't get maybe full anonymity, but you get anonymity among half the voters that cast the votes in that sense. And the same thing happens in pairs down the road. So there's no path from input to output that's complete, so you can't tell how an individual voter voted. But these servers are, if they try to cheat, will be caught with at least probability 1/2 for every time they try to cheat. More particularly, if the mixed server tries to change T votes, and if you're going to try to change an election, you want to change more than one vote. So you want to change 100 votes or 200 votes or something like that. So you want to change some reasonably large number of votes. The chance of having all of those votes unchallenged during this process goes down exponentially with the number of votes that you try to cheat on. So you have to try to change 100 votes. The chance that they'll all escape challenges will be 2 to the minus 100th. And so basically it's an exponential decay of success for the adversary, and so it becomes negligible. This is a good fit for voting, actually, because if you change 1 or 2 votes, maybe that's, it's in the noise really, but if you try to change 100 votes, it really becomes impossible. So this is a heuristic. It provides a real difficult fence for an adversary to jump over to try to cheat, given this kind of verification technique. There are other verification techniques that can also be employed if the election turns out to be very, very close, and we see some of those happen every so often. You can not only use this, but layer on top of that another challenge to the mixed servers to use one of the more complicated proof techniques. So there are ways, so basically the answer is yes, it is possible to arrange for these mixed servers to produce not only the randomized votes, the ciphertext, but a proof that they did their operation correctly in such a way that they can't cheat on this operation, either probabilistically or absolutely with these other techniques. So there's some way to get confidence that this permutation operation is being done correctly. The voter's privacy is being preserved while the integrity of that collection of votes is being preserved. Here's another idea developed by Benedita, who's a graduate student in our group, called public mixing. Cute idea. So we're not going to use the mixed servers at all. We're going to replace them by a public operation, as you'll see. So it sort of has the same idea as starting off with ciphertext for your votes, then doing a mixing operation, then doing the decryption and counting. But the mixing operation will be done by you and me and everybody else who's got a program, because it's going to be a public operation, as you'll see. So how does this happen? So this uses, again, cute mathematics. All of this stuff uses cute mathematics, right? That's one of the reasons why cryptography is fun, because you get to use lots of cute mathematics. So this uses some new mathematics for doing encrypted matrix vector multiplication. So there's a public matrix that encrypts some 0-1 permutation matrix. It's a matrix that has 1-1 in every row, 1-1 in every column, zeros elsewhere. Represents some permutation. That permutation is secret. It's developed ahead of time by some trustees in a collaborative fashion, so none of them knows what the permutation is. So it's some secret permutation. The vector of inputs is the vector of cast ballots, the ciphertext, as you saw. And we want to multiply, just do a matrix vector multiplication then, in such a way that the inputs are encrypted, the output is encrypted, but you get the result all the same. And there's this very cute encryption scheme due to Bonigo and Nissim, which supports homomorphic evaluation of polynomials of degree at most 2. That means you can do at most 1 multiplication. But if you're doing inner products, every time you do a next element in the inner product, you're doing 1 multiplication. The degree of all these results is 2 in the inputs, right? So you've got 1 element from the matrix times 1 element in the vector. So things of degree 2. And this is based on some elliptic curves. You've got two groups of G1 and G2 of the same order. The encryption looks very much like the Payer scheme that we talked about before. The count is, the 1s and 0s are represented up in the exponent. And the pairing function that you get with these bilinear maps on elliptic curves gives you that 1 multiplication, but it also tosses you into a different group G2, so you can't iterate the thing. You can't get higher degree multiplications. So it turns out you can just do matrix vector multiplication, and that's all you need. Right? So the trustees originally produced this grand matrix, which has some secret permutation in it, and they publish a proof that this encrypts a permutation matrix. So everybody can check that this is a permutation matrix. Everybody believes that at least one trustee is honest, so that nobody knows what this permutation is. So this is an n by n matrix. Each entry is the encryption of a 1 or an encryption of a 0. Right? So it's a permutation matrix, but we don't know what it is. Here's the vector that we had before. This is the same vector that we have right here of initial results. So we want to take that vector, multiply it by this permutation matrix while it's encrypted. This is where the cute mathematics comes in, right? So we multiply this by this. This is all encrypted. This is all encrypted. This comes out encrypted. We've done this matrix vector multiplication, getting encrypted ciphertext out. So this vector corresponds to what you have after all of the mixed nets. It corresponds to this column here. Right? So we have this now produces a result, and nobody knows how it's. You can do the permutation, but you don't know what the permutation you're doing. You know you're doing a permutation, and then you get this value of ciphertext. Those can be decrypted by the trustees at the end. So you can do all the hard work about setting up the permutation first. This goes very fast, and you have a encrypted set of votes then that can be decrypted by the trustees and do the final counting. Okay, so those are sort of that finishes the section on the crypto idea. So there's a lot of interesting stuff happening in voting technology, some of it crypto-based. I hope you find this part of the talk interesting just because of the acute use of mathematics and so on too, and the formulations of the problem. It seems that we really can, I think, come up with crypto schemes that give us some confidence that what you start off with in your head really mattered to the result at the end. So it's qualitatively different kind of voting systems than many of the traditional ones. The traditional ones say we trust the voting results because we trust the equipment, and we trust the equipment because it's been certified and developed by good guys and hasn't been tampered with, et cetera, et cetera, et cetera. And that's a long chain of reasoning to believe that the voting system really is secure. So you trust the votes because you trust the whole system. This says we trust the results because we can check the results. Right? We can check. We don't care what equipment it was run on. We can see that the results are actually done properly. The intermediate machines are proving that they're doing the computation they should be doing, and that's why we can trust the results. So it's qualitatively, I think, an improvement over many of the traditional approaches, but it's got some awkward spots too in terms of usability and so on. I think I've got a couple more minutes. What was it, 3:22 I should. So let me just talk a little bit. I'm also on this committee, as Professor Lee mentioned, on standards. So if you're interested in voting, but maybe don't care about the crypto, I mean, there's lots of things to think about voting. And if you think about how you want to develop standards for voting, as I have been doing for a while, you see that there's just many, many aspects that need work, technical work, policy work, all kinds of things. So the Election Assistance Commission is trying to develop the next set of standards, which is an improvement over the current set, but there's lots more work to be done. And let me mention a number of the issues that come into play when you think about voting system standards. And many of these are good areas for research in one aspect or another, because they're hard questions to address. Voter verified paper audit trails, we've already talked about. How do you do those well so that people really pay attention to them and they're done in the best possible way? Wireless, should you have wireless at all in voting systems? That's some of the issues we're thinking about. Some of the vendors are producing voting systems that have wireless units in them. It's a little bit scary. Source code availability. This has been an issue with in North Carolina just this past week, right, where Diebold was at first withdrew from the bidding because it didn't want to put its source code in escrow for this. Should standards mandate source code availability? Should it be public? Good policy questions there. Documentation requirements. What kind of documentation should a vendor supply with this voting system to persuade the certifiers that they've done a good job? What kind of level of proofs go with that? How do you set up as a part of a standard Tiger team evaluations? Who should do the evaluation? what level of evaluation should they do? What level of skills are needed for the evaluation team? How much effort? What happens to the results of that? Best practices for voting systems. COTS software, this is part of the issue that came up in North Carolina again. If you're building a voting system on top of Windows, Windows or some other operating system, that's got vulnerabilities, how do you deal with that from any kind of standardization process? How do you deal with patches to the system? How do you deal with certification of a system that's built on top of something that's that complicated? That's a real problem. The use of cryptography, some of the crypto schemes that we're talking about here are not something that anybody can check. I mean, you need to be really reasonably adept at the crypto to be able to verify that the scheme does what it says it does and the code does what the scheme is supposed to do. So you need to have special, and that's a problem too in terms of credibility sometimes with schemes. Standardized data formats, can we have interoperability between different vendors' things? You're having systems which store multiple ballots. What's the right philosophy of thinking about a voting system that's got both a paper record and electronic record, maybe another electronic record? Software development standards, those for security purposes, those are very useful, or should be, but we don't see much of that in this industry. Avionics, you see a lot of that. If you're developing systems for airplanes, they put a lot of care into how they develop their software. Nowhere near that level of care as happens in the voting industry at this stage. Software distribution, how do you know that the software that's being distributed is the software that it should be? You use hash codes and so on to help verify that. How do you know that the voting system that's set up and running the morning of the election is running the software that it should be? How do you check that the setup was done properly? Remote voting, absentee voting. There's lots of kinds of remote voting. So voting with paper, voting with electronically. This is an area where I have lots of problems just because I really like the idea of having the voter having a moment of privacy in the poll site so they can make their final choices and cast their vote free of any coercion or bribery or whatever. If you're voting at home, voting at your job, voting at the local bar, whatever, you may be selling your vote, you may be coerced in one way or the other. So I think that remote voting in general is not a great idea. Remote internet voting is even worse because you've got all the problems of remote voting with all the problems of computer security that go with that. So I urge caution on that front. Using standardized computer security evaluation procedures, how do you disclose the results of an evaluation? How do you decertify systems that have been shown to have vulnerabilities? How do you maintain good databases of problems and so on? So lots of things to think about in the voting area. So it's a nice problem area. There's many, many angles, no matter what your area of expertise is. There's some aspect of voting that you're all voters, and so you all care about this too. Right? But there's lots of technical questions as to how to design good voting systems. We are far from where we ought to be in having good voting systems in this country. And I hope some of you will think about it and maybe make some contributions towards making us have better voting systems. So to conclude, we're in a state of transition. It's clearly that we're going to more electronic voting systems. Paper may still play some role. But it seems to have possible, at least now, demonstrated in principle, that we might have electronic voting without having to trust the voting machines for their integrity. That is, they're challenged to prove their integrity, that they're doing the right things along the way. And that's qualitatively different and interesting. Without using paper ballots for recounts, so we don't need the paper as a backup there, just maybe to check that your ciphertext is posted properly, and without revealing how any voter votes. So, but how do we do this well? And as I said, there's lots of good research to be done here, and I encourage you to think about this if you're looking for research topics. So thank you for your attention. Be happy to answer any questions if you maybe have.
How soon do you envision new voting machines being available?
They're available now. If you talk to the vendors, they have lots of stuff that's available.
Stuff that you're researching?
Well, I think as you see, this is stuff which is new. It's not representative of the product, except for one company that I know of that makes something that's related to this, NDNet's company. It's something where the user interfaces need work. I think these things are down the road a bit, probably. It takes a while for new technology to be accepted too. People have to look at the crypto and say, yeah, this crypto really works, and have a lot of different experts look at it, look at the user interfaces and so on. And it may not be the best choice in the end. I mean, this crypto, I like the crypto, clearly. I think it provides a lot of nice things, but there are some penalties you pay in terms of complexity. in terms of user interface and so on too, that sort of checking that your vote is cast the right way. Maybe that's going to be too much of a problem. I don't know. So there's a real open questions here as to, so this is not a silver bullet that's necessarily going to take over the industry. It might be the right path forward, it might not be. We need research to figure out what's the right way to do voting systems. But these things, I think we need to have an environment where people are trying out lots of ideas, building voting systems. That's part of the problem with standards too. You don't want to have a standard that's too constrictive and precludes innovation. So, but I think this direction over the next 5 years, 10 years, maybe will be represented more and more in products. There's other tried and true technologies that are still popular and still quite usable. I mean, the optical scan equipment and so on too. You have the paper record is a nice technology, still very popular. So we'll see what happens. But as a research area, the main point here is a research area. This is a wonderful research. It's a hard problem. It's a messy problem. There's lots of aspects to it, depending on what your specialty is, whether it's a crypto or there's a computer security or usability in some way. There's just lots and lots of good hard questions to ask on here. So it's a fertile area for thinking about things to work on. Yeah.
The New York Times did an editorial about the complexity and accuracy of the slot machines in Las Vegas. And apparently, they're much more complex and accurate. And do you know anything about the? I
know a little bit about that. I mean, if you point to other industries and say where could the voting industry derive models for doing things better, you end up looking in places like that. Avionics is one, the gambling industry is another, the slot machines other. Both of those industries are characterized by a very high rate of investment in security specifically and careful management. In the gambling industry, I hear that they spend per gambling machine, slot machine, about 2% of the take of that machine on security. Not the cost of the machine, but the take of that machine, which is a huge number. I mean, you're talking orders of magnitude more than we spend on security in the voting system industry. So I think we do have a lot of technology developed that helps develop careful, secure systems. That's a lot more expensive than we've been willing to spend so far in the voting industry. I think we need to actually spend a lot more in the voting industry to develop the kind of security we need.
And do you know anything about how the slot machine computer works? I mean,
No. The dials come on. It's not random though. I do know that I went to, my kids were just of age, so they can come to the casino. I said, I'm going to show you this thing's a big ripoff. And I went into the slot machine and showed my kids. I put a quarter in and I won, So it's not random.
My understanding is the aisle slot machines are better odds than the ones that are in the middle.
Yeah, my wife believes the same thing. Yeah, so I think that's true. I think it's true. Other questions? Yeah.
It seems that except for this new criterion that you have of not using paper ballots for recounts, but of your original criteria that the optical scan does currently meet all those. Is that correct?
Optical scan is a nice technology. You've got the paper record that you can use for recounts. It's something where the voter can directly verify the so cast as intended is sort of obviously verifiable there. But then you've got a couple of things happen. You've got the transition to electronics because you've got a scanner there, so you're creating a copy of the ballot there. So that process needs to be carefully controlled and secure. So you could have a scanner which is taking the ballots and producing the wrong results. And then after that, both the ballots themselves and the electronics counts could be manipulated by somebody. So you don't have end-to-end security. With the kind of cryptographic schemes we're talking about here, that piece of ciphertext that you submitted that you got a printout for really matters in the final result, because not only is the casting done in a way that you can see, but you can see that the final result is verifiably dependent upon your input. So the OpScan doesn't have that property. You're trusting the people managing the process to keep the paper ballots and the electronic counts, keep the integrity of those portions of the. So it's the first part it handles pretty well, though, just knowing that your vote was cast as intended. But from there on, you're trusting the system.
So we have a reception outside, and you can talk with Professor Rivest if any question you have then. So let's thank Professor Rivest again.
Thank you for your attention.